Yeah, we'd like to welcome our first speaker, Francesco Cosentino, who's going to talk to us about acceleration of descent-based optimization algorithms via Caratheodory's theorem. Take it away. Open the meeting.
Thank you guys. Thanks for the opportunity to talk. Today I'm gonna present to you two recent work we have just finalized in collaboration with Caratheodory and Alessandro Abate. Sorry, please. Okay. So after the introduction, where I will briefly introduce you to the recombination problem, the work is mainly divided in two parts. In the first one, I will show you a geometric characterization of the barycenter of a convex hull and by means of cone, and then I will introduce a random algorithm to compute the recombined measure. And then I will show you the link between the Caratheodory's theorem and how we can use this to accelerate descent algorithm for optimization. So this is the Chakalov theorem, and it is stated for discrete probability measure. It could be extended to continuous measure as well. And essentially it says that given big N points and small n number of functions, we can build and a measure of mu on the endpoints. We can build another measure at mu, which has support strictly included in the measure of mu, and only on small n plus 1 points, such that the expectation on the small n number of function is matched exactly. In the discrete case, this can be also proved by the more famous, let's say, Caratheodory's theorem, which essentially says that any point in the convex hull of big N points can be stated as a convex linear combination of at most small n plus 1 points. So in the literature have been presented different algorithms to compute such a recombined measure, and essentially the first one, which is also the easiest one, consists in solving big N number of times a linear constraint system, which results in a complexity of big N small n cube. But then later Alliance in the 2012, using a divide and conquer paradigm, also called then hierarchical clustering, they were able to reduce the complexity with a logarithmic factor in the number of points. And essentially the technique is to subdivide a number of points in subgroups and then solving the recombination problem for the subgroups and then continuing this way. So that's why we have the logarithmic factor in the number of points. They use it for the curvature of the Wiener space, but then Maloof in the 19, they've presented a similar algorithm for a different application. Then Chernyshova in the 16 improves actually the complexity of Lyons and Litterer, getting a computational complexity n cube in the number of functions. And today we are gonna see a different strategy, which essentially try to smartly sample the solution given this geometric characterization by cones. These algorithms we will see can be combined also with the previous algorithm in such sense. So let's start with this figure. And well, here we can see that we are after the application of the functions, and here we are in a simple example where the number of functions are just 2, so we are in a 2-dimensional case. We have given the blue points, and the red point is the barycenter given the measure mu. We suppose without loss of generality that the barycenter is into the region. As we can see from the figure on the left, probably there are more than one solution, where a solution in this case is given by a triangle such that the red point is included into this convex hull. And on the right, we can try to see the characterization we will give for general dimension, where essentially we can think in this way. We can sample 2 random points between the blue one, which are the yellow and the purple one. And then we can build this infinite triangle on the top left, which we will call cone. And the the negative cone, which will be the infinite triangle on the bottom right. What can be noticed at this point is that essentially any point into the negative cone, which is, I repeat, the bottom right, plus the 2 points yellow and purple will be a solution to the recombination problem, because we'll form a triangle such that the red point is strictly included into the convex hull. This means that by simple convex geometry, we can build a measure and test a convex combination and state the red point as a convex combination of these 3 points. So now defining the cone as usually, and the negative cone, which is the cone where the basis, so the vector x, is just composed by the negative vectors of the previous one, we can state and generalize the result I just explained to the figure with this theorem. Here, well, this theorem essentially gives the characterization with item 3. We can say that Hx is a matrix where the row are essentially the coefficient of some carefully built hyperplanes, where A instead is the matrix such that it represents the changement of basis between the set both x and the orthonormal basis. What we can say is that item 1 essentially is also a particular case of the more famous Well theorem, but we didn't use it to prove this. Item 2 gives a boost in the computational, from an implementation point of view, because essentially say that we don't need to build H, but it is enough to use A, which is just an inverse of some particular matrix. And then item 3 gives us the characterization, where we have an if and only if, that essentially say that if the inverse cone is empty, we can say that 0 is not inside the convex hull of these n+1 points. And well, what we can say now is that theorem 4 implies a robustness result for the solution. This means that when we say robustness, it means that we can consider 2 different sets of big N points where there is a sort of relation between them. And we want to understand where, if these 2 sets of points are close enough, where the solution of the first one, let's say, could be also represented in some way as a solution of the second one. This, we have proved this in the paper. Then this theorem introduces a very naive algorithm, which is essentially we can, given that we want to find n+1 points, we can pick up randomly small n points, build the cone, the inverse cone, checking if the inverse cone is empty or not. If it is not empty, we have a solution. If not, we have to sample again and again and again. But at the same time, there is an optimized algorithm that we can build, and essentially is given by this strategy, which unfortunately it worked. We were able to prove this only for dimension 2. And essentially it says that if we define the basis of the cone, so if we, instead of picking randomly the first 2 points in dimension 2 that we saw before, so the yellow and the purple one, we take the first one randomly, which is x1 star, and then we take the second one such that we maximize the angle respect to the barycenter. Then we can say that 0, which was our barycenter, there exists a combination such that 0 is the barycenter if and only if there exists a point into the negative cone of the respect to the basis we have just built. And actually, although this is just for the case n equal to 2, we can use this to accelerate the block coordinate descent algorithm, as we will see. Unfortunately, we don't think this can be generalized easily, because we run into a problem of positive independent vector, and it seems that you can build any set of positive independent vector of any cardinality you want. So we think that this is related to the fact that we were not able to generalize this theorem. And this is the resulting algorithm. So now we can say that essentially it is important to underline that we can mix this algorithm with the divide and conquer paradigm, or the hierarchical clustering introduced by Terry. It is a bit a subtle thing to do, but we have done it and it works. So introduce a logarithmic factor in the number of points. Then we can mix this algorithm with the classical reset strategy for general randomized algorithm, which improve the expectation of the complexity. And third, we can combine this also with the deterministic algorithm in the sense that we can run this algorithm up to a certain number of iterations, and then if the solution will not be found, then we can stop it and run a deterministic algorithm to find the solution. So now let's see how we can link this work with the acceleration of descent algorithm. Usually in statistics, machine learning, or optimization, what we want to do is to minimize a certain loss function which is given with a certain data set xy. So we want to minimize it into some parameter theta, and therefore what we want to do is, at the end of the day, is to find the theta star given like the arc mean of the expectation, where at this point we don't know the true measure on the point. So what we want to what we will do is essentially to minimize what is called the empirical risk, which essentially gives the same measure to any point, which is an uniform. So if we now call z this random variable which take values on xi, yi, and gives the same probability to any points, we came up with the so-called minimization of the empirical risk given a loss function. Now, what can be said is that if L is smooth convex with bounded derivative, more or less, we can say that the gradient descent converge up to the choice of the learning rate gamma. The learning rate must be small enough. Essentially, it is related with the value of the Lipschitz constant of the loss function. So now we can introduce the acceleration. So we want to initialize theta 0 in Rn. Then what we want to do is essentially that we can build a new random variable at z, which is given, I mean, we know there exists thanks to the Caratheodory theorem and the Chakalov one. And it is important to remark at this point that while z is based on big N points, at z will be based only on small n plus 1 point. So it would be a huge reduction into the complexity. Now we can define the same iteration as per the gradient descent, but instead of using z, we would use at z. And in particular, it follows the theta 1 is exactly the same as the theta at 1 is exactly the same as theta 1, where theta 1 was the one of the computed with the gradient descent. And this is because we know that the gradient is exactly matched thanks to the Caratheodory theorem. But now there is a problem because we know that at the first step, the gradient is exactly matched, but then we don't know anything else. So what we can expect essentially is that if the loss function is smooth and bounded, we can say that these two at the next step, also if we don't use any more z, the gradient of z hat would be a sort of good approximation of the true gradient for reasonable choice of gamma. But anyway, we need a control statistic that will tell us when we have to recompute or rebuild a new random variable at z1, because at some point the difference will be too much and we can start to increase our loss function whilst we want to decrease it. And it comes up that essentially this one seems to be a reasonable choice. So we can introduce the stopping time tau1 and the value, the function delta, which is a Taylor expansion of our loss function. And essentially the tau1 say us that the loss function continue to decrease. Once it happens that condition, it means that the loss function start to increase, and then it means that it is enough and we can recompute a new measure. This is the resulting algorithm. It is difficult to say a priori how many times we will use their combined measure. So this is why it is difficult to do a comparison to the complexity, but we will show that in the experiment we have done, we saw some improvements. In this algorithm, it is important to remark that in step 5, we can use any recombination algorithm. So we use our, but because it shows some slightly better performance when the small n is small and the big N is huge, but it can be use any algorithm. And in particular here, we're supposed to have this T functional, which means it is an oracle that, given the history, tells us which is the direction to follow to decrease the loss function. So we were able to prove these two theorems then, that given essentially any oracle direction D, algorithm 2 will converge thanks to the definition of the control statistic. And in particular, if T is given as minus G, where G, remember, is the gradient, we can say that the rate of convergence is the same as the one of the gradient descent up to this constant big J, where big J is the number of, is related with the number of times we use the recombined measure. So these are the first experiment, and essentially, given that we reduce the number of points on which the measure is based, we can believe that if we increase the number of points big N, the improvement will be higher. And this is what is shown on the bottom figures. So in this experiment, what we want to do is to classify the blue or the red points, and then we run the gradient descent up to a certain level of the gradient, and then we run the accelerated Caratheodory gradient descent to get the same value of the gradient descent, of the gradient reached with the gradient descent. And as can be seen, we can get an acceleration up to 35 times. And well, this is dependent on the number of points and on the value of the step, but it can be said that when the step is quite small and the number of points is very big, we can see an important improvement. Now there is the major drawback of the recombination algorithm, because essentially we have to remember that the complexity in the number of functions n, which is the complexity in the dimension of the parameters we want to optimize, is at the base is n cubed. So I think we should resort in some sense to the block coordinate descent methods. The block coordinate descent method essentially says, instead of doing the gradient descent respect to any direction, we can just consider a subset of direction and do the optimization and then change these blocks. It's important to remember that the BCD can be parallelized, and one of the main aspects of the BCD is how to choose these blocks of directions. And essentially, one of the most famous rule is the Gauss-Seifel, which is based on the magnitude of the gradient. If we cannot compute the full gradient, the only possibilities we have is to do randomly selection of this block dimension and then change them at any iteration. And in this case, we can explore the special case small n equal to 2 of dimension of theorem 5, because we can decide for the dimension of the blocks to be just 2. And here there are the results on certain data set. Here we implemented also a momentum strategy for the Caratheodory BCD, and we compared the Caratheodory acceleration with Adam or SAG, which are, let's say, state-of-the-art for stochastic gradient descent algorithm. And here it can be seen that, I mean, the data set have a huge number of data, and it can be seen that essentially our acceleration is quite faster than the stochastic gradient descent. We want to still improve it with choosing carefully the step size, but I think that there's not much improvement we can do on these data set. We have to try to increase the number of functions then. So thank you for the attention.